Nuclear fusion is a process in which two atomic nuclei combine to form a heavier nucleus. This process releases a significant amount of energy in the form of heat and light, making it a potential source of clean energy for human use. The energy released during nuclear fusion is due to the conversion of a small amount of the mass of the participating nuclei into energy, as described by Einstein's famous equation E=mc2. The energy released in this process is far greater than that of chemical reactions and is responsible for the high temperatures and pressures required for fusion reactions to occur. The most common type of nuclear fusion reaction involves the fusion of two isotopes of hydrogen, deuterium and tritium. Deuterium is a stable isotope of hydrogen that contains one neutron and one proton in its nucleus, while tritium is a radioactive isotope of hydrogen that contains one proton and two neutrons in its nucleus. When deuterium and tritium are brought together under high temperatures and pressures, they can combine to form a helium nucleus, two protons and two neutrons, and a fast-moving neutron. This reaction releases a large amount of energy in the form of high-energy photons and kinetic energy. The reaction occurs in a plasma, which is a gas-like state of matter in which the atoms are ionized and the electrons and nuclei are separated. In order to achieve the high temperatures and pressures required for nuclear fusion, the plasma must be confined and heated to millions of degrees Celsius. There are two main approaches to achieving this: magnetic confinement and inertial confinement. In magnetic confinement, a strong magnetic field is used to confine and control the plasma, which is heated by various methods, such as radio waves or particle beams. The most well-known example of this approach is the tokamak, which is a toroidal, donut-shaped device that uses a magnetic field to confine and control the plasma. In inertial confinement, the plasma is heated and compressed by intense laser beams, causing the nuclei to fuse together. This approach is typically used in laboratory settings and is still in the experimental stage. Despite the potential benefits of nuclear fusion as a source of clean energy, achieving sustained and controlled nuclear fusion on Earth has proven to be a significant technological challenge. The high temperatures, pressures, and confinement of the reacting plasma require advanced engineering and materials, and there are still many scientific and technical hurdles to overcome. Nevertheless, research and development efforts continue, with the hope of one day harnessing the power of nuclear fusion for energy production.